Okay. So the study of particle acceleration in high-energy astrophysical sources capable of releasing powerful electromagnetic radiation, such as jets in active galactic nuclei, supernova remnants, pulsar wind nebulae, and gamma-ray bursts, is of important relevance for the interpretation of the observed spectra from these astrophysical objects. Indeed, much of the energy output from this astrophysical object features a non-thermal signature that is originated by high-energy astrophysical particles. Here on the left, you see the typical spectra of an AGN that is characterized by a double-bump trend, in which the low energy part is due to the synchrotron emission, while the high energy part is due to the inverse Compton mechanism. Here on the right, you see the typical spectra of a gamma-ray burst, and as you can see, it covers several order of magnitude of energy. Indeed, this non-thermal emission has been observed from the radio to the gamma-ray wavebands. So it is of crucial importance to have a real comparison between the theoretical model and the observed data in order to understand how particles really accelerate and produce the emission spectra that we observed. However, theoretical models are still under investigation. The most promising particle acceleration mechanism is magnetic reconnection. In fact, we know that magnetic fields are ubiquitous in the cosmos, and magnetic reconnection does play a fundamental role in solar space and astrophysical problems. For this mechanism to operate, the magnetic field has one component that reverses its polarity, and such a field can be established by a current sheet J moving on an infinite plane perpendicular and outgoing from the screen. Then the Lorentz force J cross P pulls the plasma towards the magnetic field neutral region, the green line, and then magnetic field line of opposite polarities rapidly annihilate, as you can see here, and magnetic energy is converted into kinetic and thermal energy of the plasma, becoming available in creating a non-thermal population of accelerated particles. For this mechanism to operate, the plasma must be resistive. Otherwise, a magnetic field line could not change their topology and cannot be cut and sew together. Sweet and Parker model describes magnetic reconnection, but it predicts reconnection rates that are associated with this adimensional number, S, that is the Lundquist number, that are several order of magnitudes lower than the observed one. In the previous slide, I talked about resistivity. Well, resistivity appears in the definition of the Lundquist number, and it is the inverse of the conductivity of the plasma. Here you see also the Alfvén velocity, and L is the typical length of an astrophysical system. We know that astrophysical plasmas are characterized by a large value of the Lundquist number. In fact, for example, in the solar corona, the Lundquist number is equals to 10 to 12. So classical steady models fails to predict the observed bursty phenomena, such as the solar flares. However, a different picture emerges when magnetic reconnection occurs as a time-dependent and unstable process triggered by dynamical instabilities as the tearing mode. In fact, this instability fragments an initially neutral current sheet into a number of X points, the blue point, and O points, the red points. In the X point, the field line cross each other and the magnetic field has null points, while the electric field is very strong. The O points are often called plasmoids and are regions of high current density. After the current sheet is fragmented into a number of plasmoids, they begin to merge, and at the end, we find only one large magnetic island. And particle acceleration can occur when particles crosses X points, or during plasmoid merging, or when particles are finally trapped inside the largest magnetic island. So the magnetohydrodynamic model constitutes the simplest phenomenological model to describe a plasma. Here you see the continuity, the momentum, and the energy equation conservation laws for this model. The magnetic field is evolved through the Faraday condition, accompanied by the solenoidal condition, while the electric field is given by this relation. So let's focus on the definition of the electric field in the MHD case. As you can see here, the electric field is composed by two terms. The first one, the red one, is the convective term. This is linked to the motion of the plasma, while the second one is the resistive term and is, of course, linked to the plasma resistivity. These two terms are linked to two different temporal scales, and the ratio between these two temporal scales give us, again, the Lundquist number. This number characterizes two different regimes, the ideal regime in which the resistivity is equal to 0, so magnetic reconnection should not be triggered in this case, and the resistive regime in which the resistivity is, of course, different from 0. Albeit astrophysical plasmas are essentially ideal, the flow evolution may lead to the formation of localized regions of large gradients and electric current in which the resistivity cannot be anymore neglected. The MHD model describes the thermal components of a plasma, but we know that plasmas are also composed by a non-thermal component represented by charged particles. So we have to insert in our model this particle equation of motion. Particles follows the electromagnetic field of the MHD fluid, and as I said before, the electric field is composed by two terms. However, which of the two terms dominates in accelerating particles is to date still under debate. So one of the goals of my work was to quantify the relative importance of these two terms in order to understand if, when, and why one contribution prevails over the other in accelerating particles. So due to the large number of equations to be solved for the particles and for the fluid, the study of particle acceleration is carried out through numerical simulation with different numerical approaches, as the magnetohydrodynamic one and the particle in cell one, that works in different spatial and temporal scales, as you can see here. In fact, the magnetohydrodynamic model works on large scale, larger than the Larmus radius of the particles, so they ignore all the kinetic effects that are relevant at the microscale. On the other hand, PCODES works on smaller scale, as they need to resolve the plasma skin depth, that is several order of magnitude lower than the typical size of an astrophysical object. So these codes are too expensive to describe the large-scale dynamics of astrophysical plasmas. Fortunately, there are also hybrid codes like the MHD-PIC1, that is the one used in my thesis work, and in which the particles are treated kinetically using a PIC approach, while the fluid is treated using an MHD model. In my work, I consider test particles. That means that there is no back reaction on the fluid, so the fluid exerts a force on the particles, but the particles does not exert a force on the fluid. This approach is implemented in the Pluto code. So the initial configuration considers a bidimensional rectangular domain of size L and half L with a grid resolution NX and half NX respectively. The equilibrium magnetic field follows a Harry sheet profile in which A denotes the initial width of the current sheet. Our unit velocity is the half N velocity, so the magnetic field strength and the initial density are equal to 1. And we have an initial pressure balance condition in which beta, that is the ratio between the thermal and the magnetic pressure, is equal to 0.01 in all our simulation. So we always consider a highly magnetized plasma. For convenience, the resistivity eta is prescribed from S bar, that is the Lundquist number corresponding to the initial current sheet width A. This equilibrium condition is perturbed by inserting a fixed number of small amplitude modes. And finally, our conditions, we have a periodic condition along the X direction and the reflective condition along the Y direction. Test particles are evenly assigned to grid zone with one test particle per cell, and their initial velocity follows a Maxwellian distribution. For the diagnostic, we also decided to save for each particle the total energy gained by the particle due to the convective in red and resistive electric field. So now let's see the background plasma evolution without considering the test particles for now. Here in this video, you will see on the top panel the plasma pressure evolution over time, while in the lower panel, you see the growth of the perturbation over time. you will see 4 evolutionary stages marked by 4 different colors. So at the beginning, the current sheet starts to shrink at the edges of the computational domain during the first linear phase. The process continues, and we can see a large plasmoid here during the second linear phase. Then the current sheet fragments into a number of plasmoids that begin to merge. At the end, the system reaches a saturation phase in which only a large magnetic island is present, and the growth of the perturbation remains approximately constant. So we decided to study the growth of the perturbation for a different value of the Lundquist number equals to 10 to 3, 10 to 4, and 10 to 5, and for different grid resolution marked by the different colors. So we see that as the Lundquist number is increased, so if we go from the left to the right, convergence is achieved at higher and higher grid resolution. In fact, we have found this relation for the threshold convergence, and we can see that we need at least 10 points on the initial scale length of the current sheet. In fact, if we look at this case, the lower Lundquist number case, we need 3 points on the initial current sheet width to reach convergence during the first linear phase. But if the Lundquist number is equals to 10 to 5, we need at least 30 points on the initial current sheet length. Now, let's consider also the test particles that evolves concurrently with the fluid. Here in the top panel, you will see the plasma pressure evolution again in grayscale, with superimposed the most energetic particle position over time, colored according to its kinetic energy. In the lower panel, you will see the kinetic energy history of the particles. So the particle will accelerate when it first crosses an X point, then due to the repeated island merging, and finally it is trapped inside the largest magnetic island that is contracting. So it is accelerated by the Fermi mechanism. Now let's consider all the particles. In fact, here on the left, you see the particle spectral energy distribution that changes colors as time grows. So at the beginning, you see that the power law spectra show a Maxwellian trend, as we expected, but as time grows, a power law appears, followed by a high energy cutoff. So the energy range is broken into 3 portions. We have the low energy part, the power law part. In fact, the spectra can be fitted with a power law of index 1.7 and the high energy cutoff. Here on the right, you see the particle spatial distribution at an intermediate time in the top panel and at the end of the computational time in the lower panel. The particles are colored according to their kinetic energy, and the energy range are the same described here in the spectra. So we see that the low energy particles, so the blue particles, are found outside the current sheet. The power law part, the particles populating the power law part, so the orange particles, are found in the outermost part of the plasmoid, while the high energy part, the red particles, are found in the very core of the plasmoid. So here you see the particle spectra at the end of the computational time, again for different value of the redefined Lundquist number, and for different grid resolution marked by the different colors. So we found that the power law index quickly converged to a value between 1.5 and 1.7 with just 10 points on the initial current sheet width. And if the Lundquist number is equal or greater to 10 to 4, the power law index remains approximately constant. And this can be linked to the onset of the fast reconnection regime. Now let's focus on the importance of the resistive electric field term. Here you see the particle spectra at the end of the computational time for different grid resolution obtained with 2 different simulation runs. In fact, first, we decided to include the resistive electric field term in the particle equation of motion, and we obtained the red bars, the black bars. Then we decided to remove the resistive electric field term in the particle equation of motion, and we obtained the red bars. I want to stress the fact that the resistive term is always present in the MHD equation for the fluid evolution, so only the particle evolution differs. So we clearly see that if the resistive term is not considered, the maximum kinetic energy achieved by the particle is lower, within a factor of 10. So we can say that the resistive electric field contribution is fundamental in building the high energy tail. Then we decided to plot this fractional energy gained by the particles over time. And this is due to the resistive electric field. In fact, here W dot also includes the work done by the convective electric field. You see different colors here because we decided to consider only the particles that at the end of the computational time reaches at least this energy, and we repeated the plot for different grid resolution. So we clearly see that the resistive term dominates in accelerating particles in this time interval. So we decided to investigate why and where this contribution becomes so important. In this video, you see in the top panel the fluid pressure evolution over time with superimposed the most energetic particle position in white. In the lower panel, you see this fractional energy gained due to the resistive electric field for this energy threshold. So we're going to see that the particles, the resistive contribution, increases as the current sheet fragments into a number of plasmoids that begin to merge, and then the resistive contribution decreases, reaching a saturation value during the saturation phase. So we can say that the resistive contribution is important during the fragmentation phase because a number of X points is formed and particles cross these X points. And the X points are points in which the resistive electric field is very important. Also, during plasmoid merging, the contribution is important because secondary current sheet forms at the interface between two merging plasmoids, and particles are accelerated due to the anti-reconnection electric field in this secondary plasmoid. Then, when particles are trapped inside the largest magnetic island that is contracting, they are accelerated by the Fermi mechanism that it is associated with the more gradual action of the convective electric field. So also, the sun is a source of high energy particles, especially gamma rays, and the emission is observed from its halo due to the interaction between electrons from the cosmic rays and solar photons due to the inverse Compton mechanism. There is an emission also from the disk that is originated by the interaction between cosmic rays, so mostly protons, and the solar gas. But also particles are accelerated during transient energetic events like solar flare and coronal mass ejection. However, the theoretical model is still not completely clear. In fact, we can find a theoretical model for the disk emission in the 1991 paper of Seckel, Stanek, and Geiser. Sorry, the pronunciation is not correct. In which they claim that the magnetic flux tubes can reverse incoming protons deep within the solar atmosphere, where they have appreciable probability of producing gamma rays. In this way, the gamma ray flux should be greatly enhanced. They also claimed that as technology was improving, the gamma ray observatory would have been able to detect the predicted gamma ray flux. However, this model cannot fully explain the observed data collected by Fermi. In fact, here you see in green the model predicted by the gamma ray flux predicted by the theoretical model, while in black here you see the data collected by Fermi in 2011. Then you see here in red the data collected by Fermi during the solar minimum between 2008 and 2010. And in blue, you see the data collected by Fermi in 9 years between 2008 and 2017. So you clearly see that there is an inconsistencies between the theoretical expectation and the observed data. First, we see that the predicted flux is lower than the observed one between 1 and 10 gigaelectron volt. Second, the theoretical spectrum has a strange cutoff here, while the observed flux extends to higher energy. And third, there is an unexplained strange spectral dip between 30 and 50 gigaelectron volt. Four, we can see also that the observed spectra is harder than the cosmic ray spectra. So these particular features require in-depth analysis. In addition, there is also another unexpected behavior that was observed. In this plot on the left, in fact, you see the location and energy of solar gamma rays divided into two temporal beams. In fact, in the left panel, you see the data before the solar minimum, and here on the right, you see the data after the solar minimum. Moreover, we have also two different temporal beams. In fact, in the top panel, you see gamma rays with an energy between 10 and 50 gigaelectron volt. In the lower panel, you see particle gamma rays with an energy above 50 gigaelectron volt. The particular feature is that the flux coming from the poles remains approximately constant after the solar minimum, while the flux coming from the equatorial plane decreases. This is strange because we know that the solar wind velocity varies with the solar cycle. In fact, at a normal solar minimum, there are long-lasting fast solar wind spreading over a large equatorial a large angle from both poles, and while in the equatorial plane we have a slower solar wind. At a solar maximum, the distribution of the fast solar wind is should be approximately isotropic. So, in conclusion, we can say that we need a balance between physical resistivity and grid resolution to achieve convergence. And in the future, I'd like to move to more realistic 3D case with a more advanced technique as the guiding center approximation, because the number of points would be enormous in order to reach convergence. I also found that the resistive electric field contribution is fundamental in accelerating particles to high energy. And I would like also to insert a guide field, so a magnetic field along the Z axis to see if the results change. And during my postdoc at the University of Arizona, I will investigate the transport of cosmic rays, and I'll try to model the gamma ray emission observed by Fermi. As to date, there is still no model that can fully explain the emission. Okay, that's all. Thank you for your attention, and I'm here for all your questions.
Any questions from our in-person audience first?
So, what is the physical reason of the cutoff you observe? A question about the first part of it. What is the physical reason of the cutoff in the energy of the energetic particles that you see? Is it just due to the geometry, the fact that the area of the plasmoid is limited? Because I saw that the red spots in the center is still much smaller than the area. So what happens? Why do you have the cutoff? The red spot at the center becomes larger and larger, so at some point you cannot confine the particles anymore in the plasmoid, and that's why there is the cutoff, or there is something else.
Okay, the cutoff is due to the fact that we are using a periodic boundary condition. In fact, in that way, particles are trapped inside the largest magnetic island that forms at the end. But maybe if we use other boundary condition, and we want to do it in the future. Probably the plasmoid will not be there anymore, and maybe particles will not be accelerated in that way. We really don't know, but the cutoff is due to the periodic boundary condition, because we reach this saturation phase in which the energy remains substantially the same, and so this is why we obtain this.
Another question, if I can. So what is the spatial dependence of the magnetic field you have in the reflection path? So you said that you don't have a guide field, but the magnetic field itself stays on the plane of the separation.
Yes.
It depends on both coordinates, X and Y.
Yes, exactly.
And the turbulent component as well. I couldn't see if you had it.
We don't have that turbulent component. But
I think I saw a potential vector part, which had
yes,
fluctuations with the
yes, we
phase.
introduced a perturbation. I'm trying to reach the slide. Okay.
Okay, so 2D as well.
Yes, always 2D.
Yeah.
But the electric field is directed along the z-axis.
Yes. This A is the just vector potential, right?
Yes.
Okay.
Okay.
Question.
So thank you for a good talk. I actually have two questions. So when the plasma saturates, it seemed like the edges were very close to the plasma. So does it actually depend on the width of the box, simulation box? So for example, if you increase the box, will the plasma get bigger and the conclusion is different?
We never tried that, but I don't think that it would be a dependence on the y coordinates.
I see. So you think the plasma side would be same, whether or not you increase the box size?
Yes,
I see.
I think yes, but we didn't try it, so maybe it's not like this.
And also, I have a question on the particles that are trapped
Mhm.
in the plasmoid. So are there any particles that does not get trapped in the plasmoid and thus have possibility of getting deaccelerated in the future?
Okay. Particles that doesn't enter that don't enter the plasmoid are not accelerated. In fact, are the blue particles that I've shown in that plot. And for this reason, we also decided in the second part of our work, the part about the resistive contribution, to exclude all the particles that at the end of the computational time don't reach, cannot enter the plasmoid. Maybe if the computational time is longer, also the other particles starting from further the current sheet can reach the current sheet and be accelerated.
So you're saying every particle that are accelerated always ends up in the plasmoid?
Yes,
and does not
exactly.
get accelerated.
Yes.
I have a question about the power index in different Reynolds number.
Mhm.
So I saw the power index is about 127
Mhm.
in the next number for 225.
Mhm.
Question in general, the current sheet will be more turbulent in higher number case. For example, if the Reynolds number or next number had 25, you would expect more smaller patterns. So the merge will be more frequent. So my question is, how does that affect the power index? It's still the same.
Okay, so you're asking if I didn't get the question.
Okay.
I'm sorry.
So can you compare to that
This one. Okay.
now?
You're talking about this.
Yes, this one.
Okay.
So the in the lunch samples to 25 case the power index is for is 1.7.
Mhm.
Actually, if the lunch sample more than higher if you go to the 26 or 7,
Mhm.
it's more close to the solar corona environment. How much the power index?
Okay, we didn't reach the 10 to 6 case because this would require higher computational cost. So we didn't have that computational facilities in Italy. But we think that the Lundquist number should be the same because there is also the theory about the fast reconnection regime that says that growth of the perturbation remains independent from the Lundquist number. This is a theoretical model studied by, for example, Luca Del Zanna and other authors. But we think that as the Lundquist number is increased, and once the fast reconnection regime begins, the power law index should be the same and independent from the Lundquist number.
Any more questions from our in-person audience? All right, let me check online. Don't see any hands raised or anything in the chat. So if there's no additional questions, we'll thank our speaker again for that great talk.
Thank you.